Well, greetings everyone. Glad you got to go to your spring break a day or two early for whatever reason, whether you went there or whether you were on some kind of field trip or something. This is what you missed. This is what we did on Friday. We did motion problems, and we took motion problems and broke them into parametric equations and used that to answer questions. So here's what we did. Please watch. Please do the assignment and keep up. So when we had problems in Algebra 1 with projectile motion, things like hitting a baseball, shooting a cannon, hitting a golf ball, we had a rectangular kind of situation that looks something like this up here. And this is a two-variable input time, output distance above the ground, t seconds after the object is thrown or hit or whatever. And we used to graph those things and find the vertex for the maximum height. We would find when time was 0, that would be when it was first launched and after it landed, and all that kind of good stuff. So what we're going to do today is take this equation here and break it down into its horizontal aspects, that would be this, and its vertical aspects, which would be this. So we can answer questions as to how far per unit time or how high per unit time. So we get to look at this in much greater detail through parametrics. Anyway, one thing to note, that if you have something that's got this term or this coefficient, the -16, that refers to a constant which is in feet. All right, so if your problem is in feet, then it will have that coefficient. If, however, that number, -16, is replaced with -4.9, then your problem is in meters. All right? So, without any more on that, we're going to go ahead and run through one of the problems. So, example 1, suppose that a ball is thrown with an initial velocity. All right, that's your V naught. At an angle of 60 degrees, that'll be your theta, with the positive x-axis, and assume gravity is the only force acting on the object. All right, that's going to bring us back to just a couple of issues up here. First of all, if there is nothing acting on an object, then there will be no wind. So you'll note here in the horizontal aspect, it's your initial velocity times time times cosine theta, but then plus or minus the wind. In this case, if gravity is the only force acting on the object, then the quantity after that plus or minus that represents the wind would be 0. If the wind is to your back and pushing you along, that would add distance, obviously, so then you'd have plus a certain amount per unit time times time. If this was a negative quantity, then you would have the wind at your face, and that would be pushing against you and slowing you down. All right, so that's that little extra coefficient that we're talking about if we have something acting other than gravity. All right, that brings us to this term in the vertical aspect. All right, that's going to equal 0 if this is going ground to ground. Of course, normally it'll end up on the ground, but if the beginning height is on the ground, then that S naught will just be 0. But if it's a batter, or if it's for some reason that the launch of the object is not from ground to ground, or it's not starting on the ground, then this will be just 0. All right? So in example 1, they're just telling you that gravity is the only force acting on the object, so no wind. We'll just note to self, no wind. And they also don't mention starting anywhere but the ground. All right, if they're not going to mention that, you can assume ground to ground. I understand that you might look at that and say, yeah, well, that's kind of unrealistic, but you know, we don't always have perfect realism in these problems anyway. All right, so when will the ball hit the ground, given what we've got here? All right, that is going to be a function of height. Because if the ball is on the ground, that's how high it is, all right? So we're going to use the vertical aspect. And the word when is telling us to find time. So that's what we're going to do. We're going to find time, and once we have time, we can use that in order to answer questions on either height or distance, however. All right, so if we're going to use that, this will be y of t equals v naught t sine theta minus 16t squared. All right, so we can then input values. First of all, if you're on the ground, it's going to be a height of 0. All right, v naught is 50 feet per second. T is what we're solving for, sine 60 degrees minus 16t squared. And we're going to solve for t. Now the fact that we don't have this extra term at the end, the s naught value, that's going to make solving for t pretty easy because you have two terms, each with a t, and that means you can just factor out that t in order to solve for it. So 0 equals t times 50 sine 60 degrees minus 16t. All right, at this point you can split this off and set each of those two factors equal to 0, so you automatically know that it'll be on the ground at time 0, which is an interesting solution, except it's really not, and no action has taken place. So that's kind of a superfluous answer, but we can just go ahead and work with the other factor. So 0 equals 50 sine 60 degrees minus 16t. All right, we can add the 16t over, so 16t equals 50 sine 60 degrees, and just divide out the 16. All right, and that will give us t. All right, in this case, and I can't really show you a calculator, but you can check all of this work with one of your own. Time will be 2.706 seconds. All right, and that's an important value, and it's probably best that you store it. So note to self, store this value. So store it in your calculator, and that way you can recall it and then use it without any of the rounding. So you can improve the accuracy if you store it. The other option would be to go to a whole bunch of decimal places, maybe 5 or 6, and hope that that will prevent you from having rounding errors in your answer. Probably best just to go ahead and store. All right, so that's when the ball will hit the ground. It starts on the ground and it ends on the ground 2.706 seconds later. All right, so how far does the ball travel in the horizontal distance? Well, we know the total time of the flight, so we can just go ahead and since it's in the horizontal direction, we'll use the horizontal aspect. So x of t equals v naught t cosine theta, and we can just plug in values that we want. So this will be x evaluated at 2.706, or your stored value, equals 50 times 2.076, or 2.706 rather, cosine 60 degrees. And that's pretty easy. x at 2.706. Just throw that in your calculator, and again, make sure you're in degree mode. That'll be 67.658 feet. All right, so that answers that question. Okay, 2 down, a couple more to go. So when will the maximum height be obtained by the ball? Okay, you actually have 2 options for this, so I'm going to put option 1 over here, and we can do this by just calculating the vertex. So we can just go ahead and say at this point that T max will equal the opposite of B over 2A. That would be, you know, the x value, and then you could plug that in and get the y value. All right, so we'll just start out with y of t equals, and we're just going to kind of restate what we had up there. That'll be 50 t sine 60 degrees minus 16t squared, and we can list out what these various parts are. So A will be negative 16. B is going to be all of this without the t. So 50 sine 60 degrees. And C is a missing quantity. There's no just constant term tacked on there. So just FYI, C would be 0. All right? And then we can just go opposite of B over 2A. All right? That'll be the opposite of 50 sine 60 degrees divided by twice negative 16, which would be negative 32. And that'll give us 1.353 seconds. All right, that's the time it takes for you to get to the highest point in your flight. All right? So then all we have to do is just go ahead and do y at 1.353, evaluate that, and that'll just be equal to 50 times 1.353. It's not much of a 5, it's not much of a 3. Sine 60 degrees minus 16 times 1.353 squared. And that should give you what your maximum height is. So that'll be 29.297 feet. So there it is. There's your maximum height. Well, this is one way to calculate this. Now, I'm just going to put a second way up here. And just think, if we know that you're going ground to ground on this, won't that maximum be halfway through the flight? So we can just kind of note here that or the max height is halfway through the flight. All right, and we already know the time for that, so if you just take that time up here, right here that we had calculated earlier, and just divide it by 2, then we can automatically get this value without all of this, you know, involvement. So 2.706 divided by 2 is your 1.353 seconds. And once you have that, you can just, you know, plug this back in and figure out what the height is in your vertical aspect. All right, just note to self that this is not always the case. All right, it's definitely the case if you're going ground to ground, but if you are starting up from the side of a building, like some 3rd floor, and you toss it up, and then the bottom, the right-hand side of that parabola just doesn't exist. There's any number of things that wouldn't be ground to ground, and if you're not doing ground to ground, then you should use the first method. Okay? All right, so that's how you find the maximum height attained by that projectile. Now, we would be sort of remiss if we did just leave it at this and do one more example, because up here, when will the ball hit the ground, we did not have an initial height. So we were able to easily factor through this thing in order to get the time. That's not always the case. So if we do have an S0 value, then we're going to have to do quadratic formula. So here it says repeats part A, and it really should be through C, from above if the ball is thrown from an initial height of 5 feet, which is, by the way more realistic than figuring that somebody's laying on their back, you know, just flat on the ground, throwing it that way. All right? So let's go ahead and repeat this process. So then y of t equals 50t sine, and we're keeping all the other values the same, so 60 degrees minus 16t squared, but now we're adding on like a c value, so plus 5. That's your S0. All right? So now we're going to have to find t through the quadratic formula. So a will be negative 16, you know, the coefficient in front of your quadratic term. B is going to be all of this without the t, so 50 sine 60 degrees. And then we do have a valid c value, so c is going to be 5. All right, so here goes. T is going to be opposite of b, so negative 50 sine 60 degrees, plus or minus the square root, make that nice and long, of b squared. That'll be 50 sine 60 degrees squared, minus 4 times a, which is negative 16, times c, which is 5. All right, and then this whole thing will be over twice a, which will be negative 32. All right, so here t is going to give you two values. All right, negative 0.0111 seconds, and it'll also give you t equals 2.81725 seconds. And you can see that this one is really the left side of the parabola going down to the ground. Yeah, nope, that's not going to be something that we can use, but we definitely can use this. All right, so no negative times. There will be mathematically, but not so much in the real world. So then the next thing, letter B, what was that? Letter B up here was how far does the ball travel? Well, we know the total flight for it to reach the ground initially, because the initial was up in the air. So we can just go ahead and do x at 2.81725 equals 50 times 2.81725 cosine 60 degrees. All right, and so that will give you 70.4313 feet. Okay, just a quick word about rounding. Remember, you're expected to do at least 3 decimal places. So if I fly off into 5 or 4 or whatever, all of that's fine, just so long as you're not giving 2 decimal places. All right. So then C for Y max, we'll go ahead and do. Let's see. This would be T max actually. This will be the opposite of B over 2A. All right, and so that'll be the opposite of B will be negative 50 sine 60 degrees over twice A, which is negative 32. And that should look really familiar because I believe we had that up here. So this will be 1.3 1.353 feet. All right, so then you just go ahead and do y at 1.353. And you just go ahead and plug that up here for t, and you have that extra value of 5. And that will give you, I'll just spare you having to write that all out, 34.297 feet. Which ironically is the original answer that you had up here, only 5 feet higher. Or, right? So, yeah. It's kind of an interesting effect that you get out of this. I had a student in my class say, well, couldn't you take what you got up here and just add 5? And I thought, yeah, you could, but I'm guessing really that the problem itself isn't going to necessarily give you the 1 and then give you a second version of it. One thing I think I'm going to do right now is pause and check one other thing. I'll be right back. Hold on. If I can find my recording program here. There it is. All right, hang on. All right, folks, I'm back. I really wanted to just look at something in that part C in that front page, but it worked out in a different manner than I thought it would, so it's just not something I'm going to include. So we'll just move on to example 2. And this is another one, but it's going to highlight some of the graphing aspects. So here we go. We have a baseball. It's hit 3 feet above the ground, so we can just kind of note to self that that's S0. And it leaves the bat with an initial velocity, that's your V0 right there, of 150 feet per second at an angle of elevation of 20 degrees. All right, so that's the launch angle, so we'll just call that theta. All right, you have this 6 miles per hour wind is blowing in the horizontal direction. All right, so that is going to create plus or minus wind issue with the horizontal aspect. But keep in mind that that is miles per hour, and over here we have feet per second. So we have a metric here that's not compatible. We're going to have to do a little bit of a conversion. So it's against the batter. So whatever we come up with in feet per second, we're going to be subtracting it. All right, there's a 20-foot high fence 400 feet from home plate. Will the ball go over a fence and be a home run? And they want us to do a graph describing this scenario. All right, it's nice that they have this request for converting. It might not always be the case, so just be aware of the fact that the metrics don't always have to be identical, and we may have to do some conversions. So we're going to just do that. So 6 miles per hour. And we're just going to do a little bit of a dimensional analysis. So I'm just going to start out converting miles to feet. So 5,280 feet per 1 mile. Miles are going to cancel. And then we'll have 1 hour is composed of 3,600 seconds. And so hours will cancel, miles will cancel, and we should have feet per second. So this will be just about 8.8 feet per second. All right? So then it says, write some parametric equations. What I want to do here, since I seem to have everything I need for the horizontal aspect, I'm just going to go ahead and do that and then generate some time. All right? So we'll start out with 400 feet away, 0 to 400. That's going to equal 150 t cosine 20 degrees minus 8.8 t. And we should be able to get t pretty easily because there is no third item tacked on here, some constant that would force us into the quadratic formula. So we'll just go ahead and see if we can't solve this thing. So we'll factor out the t. So 150 cosine 20 degrees minus 8.8. All right. And I believe that if we just go ahead and divide out that big long piece here, 150 cosine 20 degrees minus 8.8. Divide that out to both sides. We should just go right straight to t. So let me get this written. All right. So lo and behold, t is going to be 3.02677 seconds. And again, you know, 3 places of accuracy at least, so I'm where I need to be. Okay. Now we got to just figure out that's the time it takes for it to travel horizontally 400 feet. If we plug that time in to the vertical aspect, then we should see how high that ball is at that particular time stamp. And if it's at or above 20 feet, home run. If it's below 20 feet, not a home run. All right. So let's do that. All right. So we've got y evaluated at 3.02677 equals 150 t, so 3.02677, sine 20 degrees minus 16 3 times 3.02677 squared plus 3. That plus 3 is important. It may be just enough to push it over the fence. Who knows? But anyway, let's just go ahead and see what that height actually ends up being. It will equal, if you put all that in your calculator, 11.7001 feet. So no home run. This is below 20 feet. There it is. All right, so the next thing that this is requiring us to do is to throw this into a graph of a sort. And the graphing part is not terribly super hard or involved, but there will be items that you should include in order for it to be counted as complete. Okay, so go ahead and draw yourself a rectangle, and I'm just going to hope against hope that this will draw straight lines, which sometimes it does and sometimes it doesn't. You'll have access to a ruler. Look at that. That's nice and straight. All right. So let's see. It shouldn't have popped up like that, but who cares? And okay, didn't get my timing right on that. No, I did. Okay. What you might want to do, just keep in mind that you're basically 3 feet off the ground to start. Okay, so here's a point, and you can label this 0, 3, and that'll travel parabolically to here. And this point here, this is kind of where the fence is, so we can label this 400 here. We can label this 0. And this would be the point that we just calculated. X is 400 and Y is 11.7001. All right? So that's also a point that's expected. The other point that you would expect to see would be the vertex. Now I know this is hand-drawn, so I don't know if this is the exact highest point, but we'll just go ahead and pretend it is. I mean, this is hand-drawn, so it's not going to be perfect. So we'll just come over here and do some calculating, and we'll just go ahead and do T max like we typically do. And we're not doing ground to ground, so we'll do the opposite of B over 2A. All right, and so that'll be negative 150 sine 20 degrees, and that'll be over negative 32. All right, and that'll give us the time halfway through the flight. That's 1.6032 seconds. All right. Now we're not wanting parametric ordered pairs. This is X. This is Y. So we're just going to go ahead and do X at 1.6032. And that will go back in your horizontal aspect. I'm not going to write it all out. But if you run it through your horizontal aspect, you get 44.125. Check that. That is not correct. I'm actually doing the Y here. Let me get that off of here and put in the correct. I mean, that doesn't make sense, does it? 0 to 400, that would not be halfway. So how about 211.8717? And that's feet to the right. And then if we do Y at that particular t, 1.6032, then we'll get that value I had before, 44.125 feet up. All right, so that we can label. So 211.872-ish and 44.125. Okay? And yeah, that's kind of what you need. There's no reason to put a window here because you're drawing it off of real world values, and you basically have numbers all over the place, so you have a sense of scale. That's considered done. All right? So here's what I want you to do. Go to 2B, and it says, suppose the ball in the previous example leaves the bat, and they change the angle of elevation, but all other conditions of the example remain the same. Will this be a home run? What I'd like you to do is to go ahead and pause this, work it out in your packet, get a calculator, see if you can't match up to what I get. So pause this tape and then come back. Okay, I'm going to assume that you did pause it, so here's what we're going to do. Actually, I like the blue a little better, so let's go back to the blue. Oops, hang on. Get this right. Okay, here's the first step. I'm back in the red. I'm just going to do it in red. All right, so 400 equals 150 t cosine. Now we're at 30 degrees minus 8.8 t. All right, so you just factor out the t. Just like before, you can look in your notes and see how we did it when it was 20 degrees. So 150 cosine 30 degrees minus 8.8, and then just divide out this big chunk of stuff. Do it to both sides, and you should get your time. All right, so the time to the fence for this will be 3.303 seconds. All right, put that in your vertical aspect and see if the ball went any higher than it did in the previous portion. So we'll do y of 3.303. That'll equal 150 times 3.303. Point a little clearer. Sine 60 degrees minus 16 times 3.303 squared plus 3. And this is what you should have gotten. 76.770 feet. So yes, that would be a home run. All right, so there it is. There are your notes. Hopefully things are clear in your minds, and do your homework, do the assignment, keep up. We're not delaying anything. This is a pretty straight through unit. We're spending a day on this. When you come back, we are going to do the Ferris wheel problems, and we will just go over homework, and we're not going to address this anymore. So stay up to date, and thanks for watching.